Welcome to Ask and Learn.
In part A, we want to estimate the absolute maximum and minimum values of the function exponential of x plus exponential of negative 2x on the interval 0, 1, the closed interval, using the graph of the function. And in part B, we calculate the exact maximum and minimum values of f over or on the interval 0, 1. So this is the graph of the function. We can see that we have an absolute minimum around this point, and the absolute maximum is around this point. So the absolute maximum is attained at x equal 1, as we can see here, and there is some point around here where the function attains its absolute minimum. So if we make some zooming of this graph at those regions there, so we find for the absolute minimum, let's say draw a vertical and horizontal dot line to show the absolute minimum point, and we can see that the value of that minimum is around 1.89. And that minimum occur about this value here, which is x approximately equal 0.23. That's for the absolute minimum value of the function, and for the absolute maximum value, we have this sum here around the endpoint 1, and we can see that the absolute maximum value of the function is about, we can see here, it's about 2.85 at x equal 1. In this case, we are sure that the absolute maximum value is attained at x equal 1. In this case, we know that the absolute minimum value is attained at an x approximately equal to 0.23. So these are approximations to the absolute minimum value and the x where it occurs. But now we want to calculate that precisely in part B, and for that we use calculus. So the first thing we gotta say is that if a function is continuous on a closed interval, it attains its extreme value. That is, there are points in that interval where, or such that the images of those points are equal to the maximum and minimum values of the function over that interval. That's the first thing. We know the function attains its extreme values over a closed interval, a continuous function like this. And the other thing is that we know that those extreme values are attained at either the endpoints of the interval or at critical numbers of the function in the interval. So we gotta find the critical numbers of this function to evaluate the function there and at the endpoints, and from those images we choose the largest and the smallest. So we are going to find the critical numbers of f in 0, 1. For that, we find the derivative of f, and that is the same exponential function minus 2 e to the negative 2x. And that derivative exists for every value x in the interval 0, 1. And I say that because if this is true, it implies that the only critical numbers of the function are those values of x for which the derivative is 0. So the only critical numbers of f are those values of x for which the derivative is 0. So we gotta solve this equation here. Derivative of f equals 0. So that derivative equals 0 is the same or is equivalent to e to the x minus 2e to the negative 2x equals 0, and that's equivalent to e to the x equal to 2e to the negative 2x, which is equivalent to e to the x equal to 2 over e to the 2x. We pass this denominator here to the left, and that's equivalent to e to the 3x equal to, and applying natural logarithm and taking into account the natural logarithm is an injective function, we have again equivalence with this equation. Natural logarithm of e to the 3x equal to the natural logarithm of 2, and this is equivalent to 3x, because the natural logarithm and the exponential functions are inverse to each other, equal natural logarithm of 2. And this is the same as saying that x is the natural logarithm of 2 over 3. And that's the exact value where the derivative is 0. But now we can use a calculator to find that this number is about 0.23 104 90602. So we have this solution, and as we can see, this value is inside the interval 0, 1. So it's the only critical number of f in 0, 1. And in fact, in the whole real numbers, but in 0, 1. That's what is important in this case. So we have found all the critical numbers, that is the only one that exists for the function in the interval 0, 1. So we gotta evaluate the function now at this critical point, this critical number, and the endpoints of the subinterval, that is the number 0 and 1. Then f at 0 is exponential of 0 plus exponential of negative 2 times 0, that is 2. Or if you want to be clearer, is e to the 0 plus e to the 0, that is 2. F at 1 is e to the power 1 plus e to the negative 2, or e plus e to the negative 2, and using a calculator, this is about 2.85336171117. And f at the critical number natural logarithm of 2 over 3 is equal to e to the natural logarithm of 2 over 3 plus e to the negative 2 natural logarithm of 2 over 3. And we can write this as e to the natural logarithm of 2 to the 1/3 plus e to the natural logarithm of 2 to the negative 2/3. And we know this is equal to 2 to the 1/3 plus 2 to the negative 2/3. And that's approximately equal using a calculator to 1.8898815 748. So we have these three images here, and among those images are the extreme values of the function, because we know that a continuous function attains its extreme values over a closed interval, and those points or numbers in the closed interval where the function attains those extreme values must be either critical numbers or the endpoints of the interval. In this case, we have only one critical number inside the interval 0, 1, and so we have only three options: the images of the endpoints of the interval and the image of the only critical point of f. And we can see that this is then the maximum value is 2.8536171117, and the minimum value is 1.8898815 748. So we can say that f has an absolute minimum value um, 2 to the 1/3 plus 2 to the negative 2/3 This is the exact minimum value of the function over the interval 0, 1. And we can say 0, 1. We put it in here, and we know that this value is approximately equal, as we saw above, to 1.8898815 748 on 0, 1. And if that is the absolute minimum value of the function over the interval 0, 1, which is this value here, and this is an approximation to that value, is attained at the only critical point of the function f. So I will say that here, and it occurs at the critical number x equal natural logarithm of 2 over 3. Then we have that f has an absolute maximum value, that absolute maximum is 2.85, which is e plus e to the negative 2. So it's the exact value e plus e to the negative 2, and it's about 2.8536171117 on 0, 1, and it occurs at the right endpoint at 1, that is the right endpoint, x equal 1. So we have these results, and we can see that we are in accordance to the estimation we did in part A, because the minimum is around 1.8 0.9 is we round this number to 2 decimals. And it occurs at natural logarithm of 2 over 3, which is about 0.23. And that we saw here. Absolute minimum is a critical number where the derivative is 0. And the value of the absolute minimum is around 1.89, and it occurs at about 0.23. So that is correct. And for the absolute maximum, it occurs at the writing point 1, and it's about 2.85, as we saw here. So it's in accordance to what we did in part A, but here we have the exact values, that is the absolute minimum and the absolute maximum in a closed mathematical form. 2 to the 1/3 plus 2 to the negative 2/3 for the absolute minimum value, and e plus e to the negative 2 for the absolute maximum value. And the points or numbers where those extremes occur are also exact, because we have for the absolute minimum value, x is the x where it occurs is natural logarithm of 2 over 3, and for the absolute maximum value, it occurs at x equal 1.